Okay, welcome to the today's class. Today it is lecture number 4, unit number 3. Okay, so we are going to look at the layouts. So in the last class, we have seen that with the circuit symbols, we have designed the circuit with circuit symbols. So we have created, we have designed, we have realized the circuit. The second one is in order to translate this designed circuit in actual chip or actual silicon semiconductor, we have used the concept called stick diagrams. Okay, so we have drawn the stick diagrams in terms of the MOS layers that we have seen, and and also we have seen we have to use the design rules, then only it is possible to translate your circuit into a chip. Okay, so then only it is possible to translate your circuit into the materialize the circuit in a given semiconductor. Okay, so now we are going to look at now is that how do we form a layout for a circuit. So in order to draw the layout, it's very essential to know that the symbolic circuit diagram, then related to the stick diagram, then we have to apply the design rules, then only it is possible to create the layout. Okay, so let us see how do we form a layout. So I want to create a layout. Okay, so draw the layout of an nMOS inverter. Okay, using lambda based design rules. Okay, using lambda based design rules. Okay, so what we have to do, first of all, in order to do this one, first we should know the circuit diagram. Okay, so let us draw the circuit diagram first of all. Circuit diagram. So we know very well about the circuit diagram. Quickly I can draw. Here I should consider a depletion type mode transistor, right? This is connected here. And we have to take an nMOS transistor, an enhancement nMOS transistor. This is connected to ground. This is connected to VDD. And VN is here, I should apply. And we want to get the output is V out here. Okay. Now, what is the stick diagram for this? Okay. I need to write the stick diagram. So the stick diagram contains the layer information about the elements and its interconnections with the color codes, right? So for that one, I have to draw the power lines with the help of the blue line for the power supply VDD, and this is for the ground. Okay. No, it's look like some bending thing is there. It's not like that. Okay, a little bit better. Now I have to form a transistor. This is a diffusion. Okay, sorry. For the diffusion, what is the color that we have to use? So we should use green color for diffusion, green color, and this also green color. And we have to take a polysilicon here. Here also a polysilicon. Okay, and toward the interconnection, something like this. Since the same diffusion I'm using, I'm extending the diffusion line here. Okay, now I'm extending the diffusion towards the VDD, towards the ground as well. But we should have a contact cut here. One contact is here, another contact is here. Okay, and so in order to connect this polysilicon to this point, I am using the extend in the polysilicon only. But here I should use brown color. Which color I should go for? Go for it. It's a brown color. Okay, so the brown color I should write it here. So this is called buried contact. What we can call it as buried contact. Okay. Now we extend this diffusion and the purpose of the V out. So this is called V out. Okay, and this is nothing but VAN. So if you want to show the substrate, I'm going to use crossbar. So this is the stick diagram. Now we have to apply the design rules. Okay. Now what do you mean by the design rules? Design rules that we have to apply to the stick diagram. What are the design rules? Quickly, some things that we will write here. So all the materials, all the layers, you can say that it's better, we can call it as layers. All the layers has minimum, all the layers has a minimum width of 2 lambda we have to maintain, except metal 1 and metal 2. Okay, so in case of metal 1, we have to consider this the 3 lambda. This is for 4 lambda. So that is what we have seen in the last class. What is the second point that we have to remember? The spacing between, okay, the spacing between diffusions, between the diffusions, but I have to take another color, between the diffusions is equal to, what is the value that we have seen? 3 lambda, right? Let me check without having the problem. Yes, what is the minimum spacing? 2 lambda, sorry, it's a 3 lambda for the polysilicon, 2 lambda for the metals, 3 lambda. Okay, so what we have to do is that the minimum spacing between the diffusion must be 3 lambda. Okay, 3 lambda we have to maintain. Okay, and for polysilicon, for polysilicon, this must be 2 lambda. It must be 2 lambda, and diffusion to poly. Okay, diffusion to poly, it should be 1 lambda. It should be 1 lambda we have to maintain. And metal 1 to metal 2. So sorry, better I have to consider metal between the metals. Metal 1, it should maintain 3 lambda. We should maintain 3 lambda. For metal 2, we should maintain 4 lambda. Metal 2, we should maintain 4 lambda. Okay, this is the spacing related and width related things that I have shown you that way. Okay, so this kind of information is sufficient. Let us apply these kind of rules and we can draw the layout for it. Okay. So I want to take this layout diagram here, copy, and then paste here some. Since I want to show it to you in a same manner, is the reason I'm using this diagram. Okay, so now, so let us draw the layout. Layout diagram. Okay, So what is the required? What is the required for? Okay, of course, contacts also we'll write some contact related information also. For contacts, what we have to do? Overlapped region should be overlapped region should be 4 lambda by 4 lambda. We have to maintain. Okay, and contact cut, right? Contact cut should be 2 lambda by 2 lambda. Okay, contact cut should be 2 lambda by 2 lambda. Whereas the buried contact, so let us consider the buried. Okay, so buried contact, what we have to see in that, towards diffusion side, towards diffusion sides, we should maintain 2 lambda from channel. Towards polysilicon side, 1 lambda from channel. So that's what you have to remember. So this is for very important, 1 lambda, this is 2 lambda. Okay, and the butting we are not interested to do right now, so I am not interested to write in this at this point. Okay, fine. So let us draw the layout for this. Okay, so we have to take I think it is better to take boxes. Okay, so this is the metal line, this is the one metal. Okay, for the VDD, and I'm going to consider, I'm going to consider another metal as well. Okay, so this is the 3 lambda by 3 lambda. I think this, it cannot be a 3 lambda by 3 lambda, but I want to show it in more detailed manner. Oh, sure. So I hope this could be 3 lambda. So 1, 2, 3. So, okay, let it be like 3 lambda. Okay. Same thing I want to consider. Copy and then paste it here. Please understand how to draw the layout. Please carefully have to think is that. So therefore, this is the metal line. For the sake of simplicity, I'm using the hash lines only. Okay, you can fill the color, or maybe you can use the hash lines also. So I think better I have to take this one, I think. So okay, this is the one. Please give me some time. I want to complete it. Stroke is required. Okay, now, so yeah, better I want to consider this hash lines only so that it will be useful for you to understand. So I'm going to write vertical lines. Okay, so diffusion is available from top to bottom. Okay, so here also I'm going to take color is green color. I'm going to use this one. So therefore this is actually 2 lambda. So by the by, what is the distance? What is the minimum width of this I have contained? It contained 3 lambda. Okay, so what is the minimum width of this material then? So for example, I'm writing here, this is actually 2 lambda, minimum 2 lambda I have to maintain. So, okay, now it is very important to note that, so length to width ratio for this one is 1:1 I have to consider. Here is 4:1 that I have to consider. Okay, so therefore here is actually for the depletion type MOS transistor, length at 8 lambda is required and width is 2 lambda is required. Here is 2 lambda by 2 lambda, is the length to width ratio is 2 lambda by 2 lambda. That's what we have to consider for a PMOS transistor, sorry, nMOS inverter. Okay, so therefore what I can do is that what I can do in this sense is that I have to consider one line here. I think so this is the line is meant for the channel. It's a 2 lambda channel. Okay, so that's it. So this is the VN signal that I have written here. What I'm writing here. So I'm writing the VN signal. Okay. So the length is what is the length and width ratio of this one? I have considered here is the length is. So normally this is what we are talking about. So this is the area. So normally hash lines that we are writing, right? So hash lines that we are using for the time being, or you can fill the color also. And this is the, I'm sorry, it is not that one. Yeah, diffusion is something like this. So the combined point is called a transistor. So this is the where the transistor is formed. This is where actually the transistor is formed. Okay, so what is the length and width ratio of this transistor? This side it is 2 lambda, and this side it is 2 lambda. Okay, this side also 2 lambda. So therefore 2 lambda by 2 lambda length to width ratio for the enhancement type MOS transistor defined in this way. Similarly, the width of the transistor, the length of the PMOS depletion mode transistor is 8 times should be there. Okay, that means from this point to this point we can consider, let us say in this way. Let us say in this way. Okay, so therefore what I can do is that I can take diffusion from here to here. From here to here. So therefore you can observe that the length of the transistor is 8 lambda is maintained. Length of the transistor 8 lambda is maintained. How can you say this one? So this is actually, for example, source. So this is the drain, for example. This is the source. Now source to drain distance is nothing but a channel only. Therefore it is actually 8 lambda, for example. So that means 4 times it should be. 4 times it should be. So the length of the enhancement is depletion is 4 times of the enhancement type MOS transistor. Okay, therefore I'm going to write these colors in this way. Okay, fine. So this is the channel area. Okay, so from this point to this point, this is called channel area. This point to this point is called channel area. Clear? Okay, so now I'm going to take my output. Okay, so I can take the output from here to here. Okay, from here to here, the output I should take. Okay, so can you say what is the can we use the design rules for this one? Yes, obviously the design rule is involved here. So this is actually the diffusion line. This is the polysilicon line, right? So the diffusion to polysilicon, how much distance we should maintain? Minimum of 1 lambda. So therefore minimum of 1 lambda is maintained here. Minimum 1 lambda we have to maintain. Similarly, upper also. So this is also polysilicon. This is the diffusion. So we have to maintain minimum 1 lambda. It is could look like more than 1 lambda only. So I am not showing anything about it. Okay, so far everything is perfect. So we have created the source VDD and ground, and we have created the transistors and extend the output. Fine. Now the thing is that we have to provide the contacts. Okay, so what is the contact that I should consider here is that for upper transistor, so diffusion is connected to the metal. When the diffusion is connected to the metal, what is the overlap region that we have to use? Overlap region is 4 lambda by 4 lambda. So simply, so this is how let us consider. Maybe, of course, it may be a center of this point. It doesn't mean, it doesn't matter, but above also we can write it. Okay, so therefore it is uniformity is there. If I'm right, if I'm draw like this, it is a uniformity is there. Okay, so therefore this is a 3 lambda means upper one is 0.5, 0.5 lambda, bottom one is also 0.5 lambda. So total it is a 4 lambda by 4 lambda. Okay, so it is a mixing of two colors, as you know that it is a mixing of two colors. So something like this. It is a mixing of two colors, blue as well as green. Okay, so therefore we take all these things. Oh, sorry. Okay, I think green color is not looking at. Now it is both colors are visible, I think so. Okay, sometimes it is difficult to understand, but you have to keep remember that is both lines are there. Okay, so it's a mixing of two colors. Okay, the blue as well as green, and I want to fill with all these things something like this, and vertical lines also I have to consider something like this. Okay, so what is the contact cut here? The size is 2 lambda by 2 lambda. Contact cut is required. 2 lambda by 2 lambda contact cut is required. So from contact cut to overlap region, how much distance is there? If it is a 4 lambda by 4 lambda, 2 lambda by 2 lambda, 1 lambda upwards. So from here you can see that from here to here 1 lambda, from here to here 1 lambda, from here to here 1 lambda, from here to here 1 lambda. So therefore when the contact cut is 2 lambda by 2 lambda means the overlap size is 4 lambda means the spacing between the overlap region and contact cut should be 1 lambda, maintaining all the directions. Okay, same kind of thing is required at the bottom also, contact cut. Okay, so here I'm going to consider, sorry, here I'm going to consider the same thing. So I put it here. Okay, and it should be, yeah, that color, green color. So I want to take the green color over here. Is it clear? So green and red color. So okay, now I need to cover this region with the help of hash lines and vertical lines as well. Okay, now I have to use contact cut, 2 lambda by 2 lambda contact cut. right? So that's it. We have done everything, but except at this region. Okay, at this point that we have to remember. Okay, now here we need, it requires buried contact. How do we do this one? So buried contact can be placed at the bottom. So at this point that we want to write. Okay, so this is the channel place. Okay, so the channel region, this is the entire channel region. You can see that. Okay, this is the entire channel region. Of course, we know that. So at the bottom that I want to do it here. So what we define that when we have a buried contact towards the diffusion sides, 2 lambda we have to maintain. The overlap region size I'm talking about. The overlap region size should be from the channel edge in all the directions of the diffusion, 2 lambda we have to maintain. So I have to take brown color, right? So the brown color I have to take. So this is the brown color. So here 2 lambda means something somewhere is here. So is that you can observe. So this is the brown color. So 2 lambda. So bottom is also from 2 lambda. So this is the what to 2 lambda. Bottom also 2 lambda. But towards the silicon side, towards the polysilicon side, only 1 lambda. So therefore, what I can say that, please remember. So from here to here, 2 lambda I'm maintaining. From here to here also 2 lambda I'm maintaining. Okay, because diffusion is top and bottom. But the sides, we can see that polysilicon is there. Towards the polysilicon side, 1 lambda is we have to maintain. Suppose 1 lambda is something like this. So here is actually 1 lambda. So from here to here, it is 1 lambda only. Similarly, this side also only 1 lambda I have to consider. Similarly, 1 lambda from here to here also as well. So from here to here, what is the distance between 1 lambda we have to maintain? Right? So therefore, what is the size of this overlap region? So what is the brown color overlap region? Whatever the brown color overlap region we have considered for this particular case, what is the size? So this is 4 lambda we have considered. Well, 4 lambda we got. But what about this side? What about this side? From this side to this side? So middle is 2 lambda. Right hand side, left hand side, another 1 lambda. So there is also 4 lambda. Therefore, it's a 4 lambda by 4 lambda overlap region for the contact is observed. And the center we have to consider crossbar, something like this. Center we have to use crossbar. So this is how we have to provide the buried contact for polysilicon to diffusion connection. Okay, so this information we have to give to the layout, the fabrication engineer. They will identify that yes, buried contact is required for him, like that. Clear to all of you? I hope you understand how to draw the layout for this particular from the stick diagram to layout. Okay, so once we have a layout, then only it is possible to do that one, right? So therefore, if you want to write the NAND gate, for example, what we can do? Yes, we can extend. We can extend this bottom ground to another distance, and then we have to accommodate another polysilicon. As simple as that. Okay, shall we draw the NAND gate layout diagram? Okay, I hope you understand this one. So yeah, I think better I'll write here is 2 lambda by 2 lambda. Okay, 2 lambda by 2 lambda. This is 8 lambda by 2 lambda, length to width ratio. So it is a length to width ratio. It is length to width ratio. Okay, that's what we can observe. So therefore, it's not required then. So for sake of simplicity, I'm removing this one. Delete. Okay, so put it here. Okay, fine. I think everything is clear. Okay, let us draw the NAND gate layout diagram. So the same thing that let us consider. Copy and then so similar concepts that we normally use. Therefore, better I have to consider the same thing. Copy. Paste it here. Okay, so what I can write on top of it, just only the modification of layout diagram for. So draw the layout for NAND gate, to input NAND gate. What is the circuit diagram then? Just we have to use another transistor here, right? So we have to use another transistor here. So let me now take, this is called A, this is called B, that is called V out. So we have to take okay, we have to take another polysilicon on top of it. Okay, uniformity, let us maintain the uniformity. Okay, so therefore this is called A, this is called A, this is called B. Here also, it is also 2 lambda by 2 lambda only we have to consider. Okay, design rules are the same. Now what we can do is that okay, so I'm going to extend this polysilicon here, not polysilicon, the diffusion. So from here to here, undo. So extend this towards this side. Okay, fine. Yeah, now we can draw these lines up to this point. Okay, now take another polysilicon, draw. Take another polysilicon. So backward slashes that I have to use for this one. So now, by the way, what is the distance between these two polysilicons that we have to use? So for the polysilicon 2 lambda, we have to maintain. We have to maintain minimum 2 lambda. Otherwise, design rule violation will be there. Okay, so that's what we have to remember. So that's it. This is the CMOS, sorry, nMOS NAND gate. As simple as that. Okay, I hope you understand this point. Okay, like this NAND gate, NOR gate, whatever the way the stick diagram is look like, just apply the design rules and provide the necessary thing. Okay, it's a very simple. So just we have to know how to draw the stick diagram, and from the stick diagram you can draw the layout very easily. Okay, now shall we draw the layout for CMOS inverter? Let us draw the stick diagram, sorry, layout diagram for CMOS inverter. Okay, so draw the layout for CMOS inverter. Okay, so what is the scenario that we have to follow here? What is the circuit diagram now? The circuit diagram is like this. The circuit so we have to consider a PMOS transistor. Okay, we have to consider an nMOS transistor. it is called VDD, ground. Take a common point, and that is called VN. Take a common point, that is called Vout. What is the stick diagram? Stick diagram as simple as, so let us draw quickly. Okay, so the stick diagram is something like this. We have to take the power lines by using the metal lines. Take yellow color. Take an yellow color for the entire nMOS transistor. For PMOS transistor, take the green diffusion for nMOS transistor. Use metal polysilicon and polysilicon, and use the metal to connect between these two. Use the metal to connect between these two. Okay, so better I have to consider this way. So it should be a straight line. Okay, something like this. So here the contact cut is required, as we know that. Here the contact cut is required. Here the contact cut is required. Here the contact cut is required. Okay. Of course, there is a polysilicon is also observed here. These two polysilicons are connected together, something like this. Take a common point and extend the metal here. Extend the metal here. Okay, and observe there is a substrate here also. We have the substrate connection also. We have to mention. Okay, for the nMOS transistor, we didn't mention any kind of substrate, but substrate will be there. Okay, we can observe this substrate at this point. Okay, so here it is necessary to mention whether we are following the N-well process or P-well process. That's what important. For that one, we have to use a demarcation line. So a demarcation line that we have to use. So a demarcation line. So brown color dotted line, we have to use demarcation. Demarcation line. So what we can observe that. So let me check what suitable technology that we normally use. Okay, P-well process. Let us consider. Let us consider P-well process. So P-well process means, what does it mean? P-well process means, so whatever the under the demarcation line, whatever the transistors are there, that is in the P-well. That is in the P-well. So whatever the transistors are there in this. Okay, sometimes we normally use something like this. Sometimes. So what is that? For example, N-well, if you want to use it, then we have to use the dotted line, something like this. That means that whatever the top transistors are there, those transistors are there in the well. That is N-well process that we use. I am interested to use in P-well process, therefore I don't want to use these lines, something like this. Okay. Okay. Now let us draw the layout diagram. Layout. Let us draw the layout. Yeah, carefully understand these points. Okay, first I have to draw the metal lines, as we know that. Okay, so draw the metal line here. So draw the metal line here also. So two metal lines that I have used there. Okay, fine. So better I'm going to consider these hash lines. It look nice. Okay, so yellow line is required for the upper transistor. Okay, 2 lambda by 2 lambda upper transistor is required. Okay, Okay, next, green line is also required. No, better I should take, this is the one. Copy and then paste here. Please remember that okay, so but this color should be green diffusion. Okay, fine. So between that, what is the material that we have to use? Blue color. So but it's 3 lambda size it should be. Okay, so that's the reason why I'm going to consider it 3 lambda in this way. Okay, so for the n diffusion, p diffusion 2 lambda, but the width of the PMOS transistor, width of the metal must be 3 lambda. Okay, so fine. Now I have to use some spatial lines here, but here closure lines that I have tried. But for this one, vertical lines are required, right? So something happened. Something happened. Please wait. It's stuck somewhere. Okay, now. So we have to draw the lines here. Draw the lines here. Draw the lines here. So something like this. Okay. Okay, fine. So this line is required. Okay, one transistor is formed here, 2 lambda by 2 lambda. Another transistor has to form here. So that is also 2 lambda by 2 lambda. Of course, we need to connect these two things also. How do we do this one? Okay, so I have to extend this one also to this side. So this one also we should extend. Okay, so I hope you understand what I'm trying to do this one. Oh, sorry. So better I have to take medium. Okay, this is also medium. Now I think it's perfectly all right. Okay, so this is the connection that I have to do it. Okay, so all are forward slashes, the backward slashes. Okay, so extend this one as an input. Extend this metal as well. Okay, so this is also VA and V output. Okay, so finally we have to provide the contacts there, right? So what is the contact here? Yellow contact is required and we have to provide there. So this is what What is the size of this one? 4 lambda by 4 lambda. So please remember that 4 lambda by 4 lambda. So copy. So I have to consider this one, copy, and paste it here. So this is the one region where we need to have, paste it here. So this is the place where one thing is required here as well. Okay. Consider that this is a 4 lambda. Metal is also a 4 lambda for simplicity. It doesn't mean so 3 lambda must be maintained. If you are taking the more than the one also, does not have any problem. So these are the places. Okay. So but at this particular place, oh sorry. So at this particular place, whatever the material is there, that is actually this diffusion, right? Whatever the whatever the diffusion here, again this is P diffusion. Okay, for those diffusions not have a problem. Okay, now we have to take another overlap region, mixing up the blue color. So I have to consider here as well. Okay, here I have to consider. So here I have to consider. Here also I should consider. Overlap region. Okay. So copy. Let me paste it here. So here also we need to paste. Here it should be blue color, right? So I want to take the blue color overlap region here again. That's it. Okay. So therefore here what I can do is that, so this overlap region is extended towards all these directions, something like this. Provide a metal contact there. Okay. So extend this metal contact is available here. Okay. But it requires these kind of things as well. Green. So metal contact we have to put on top of it. On top of it, we have to provide. On top of it, we have to provide all these things, right? Extend this one and a green diffusion as well. And put a metal contact there. So again, here also, it's a blue color, mixing of the blue color. Okay. And the green color. Put a metal contact there. That's all. So everything's perfect. Only thing is that body contacts are required. So what is the body for the PMOS transistor? Okay, yeah, body for the PMOS transistor is nMOS transistor, N substrate, right? So N substrate overlap region that I have to consider here. So here we have to consider nMOS body that we are considering for the PMOS transistor. Okay, and it is a mixing of two colors, as we know that. So therefore what we can do is that it is the mixing of green color and blue color. Take a common point there. Take contact cut here. So this is what we can say that substrate for the PMOS transistor. Substrate for nMOS transistor is yellow color. So I have to take a snapshot here. Okay. And blue line that I can consider. So blue I have considered there, and yellow line, yellow diffusion. Okay. So therefore now I have to take contact cut. I want to provide the contact cut in between these two. So provide the metal contact there. That's it. So this is how we have to draw the layout for the CMOS inverter. Only thing is that we have to provide the well now. How do we provide a well for this one? Okay, it should be there in the well, right? PMOS transistor should be there in the well. So for that one, we are going to use green color box. This is the green color box for this one. The green color box that we have to use for the N-well P-well process. It's a P-well process. So P-well means it is better to consider in the yellow line. Okay, so that's it. The well should be there in the nMOS transistor should be there in the well, right? So it is also possible to mention that whenever you are realizing an nMOS transistor, PMOS related things must be masked together. PMOS devices must be masked. Okay, so for that one, masks are also possible to define. Masks are also possible to define. So P plus masks are required then. Okay, so for that one, what we do is that we take a P plus mask here. We take a P plus mask here. I think better I have to extend this one. What I can do is that I can remove this portion. That is the single stroke I have to use for this. Okay, so this is what the well, this is called P well, as we know that it's a P well. And one more thing is that whenever you do the nMOS transistors, P devices must be masked together. For that one, I'm going to use another P plus mask, something like this. I have to use P plus mask. Similarly, I have to cover this entire region also. I have to cover this region also. So these are also P diffusions only, right? This is. So what is we can call this is P plus mask. So we are saying that don't do all the things at the same time. Use mask well during other materials to form. Okay. So this is also P plus mask. So here we have to follow one design rule. Okay. So what is the design rule for the overlap region to this particular region? So that's very important to note that. So this overlap region to this one, we have to maintain some distance. What is that? How much distance that we have to maintain? Okay, so we have to maintain all the directions by minimum 2 lambda. Minimum 2 lambda that we have to maintain. Okay, so therefore here is 2 lambda we have to maintain. Here also 2 lambda we have to maintain. Here also we have to maintain the 2 lambda. So except this side, except towards this contact side, there is no design rule. But in all the directions, so that means here the top right side, bottom side, we have to maintain minimum 2 lambda from the overlap region for the P plus. Okay, so therefore what is the design rule that we specifically talking about? For a P plus mask to overlap region, we should maintain 2 lambda. Okay, except towards contact and diffusion contact. I can write it as end diffusion contact. End diffusion contact. Right? That's it. And one more thing is that the distance from this P mask to P plus mask to this one, we should maintain minimum 1 lambda. Of course, it is more than 1 lambda, but we have to maintain minimum 1 lambda. So therefore, another thing is that from P plus mask to P well, we should use minimum 1 lambda. Maximum can be anything. So, but minimum should be 1 lambda. Okay. So these are the design rules that we have to follow, addition to the normal rules. So this is what we have to carefully understand. Okay, so these are the CMOS design rules. So I can simply write it CMOS design rules. Normally these are called CMOS design rules, demarcation line related thing, and as well as this one also. So here I can write here, I can paste it here. So this is the CMOS design rules. CMOS design rules. Yeah, I hope you understand the concept that whatever I have done here. Okay, of course, because of notes I want to give, so I put it here itself. Okay, CMOS design rules. So with this, we have come to the end of the today's session, and please go through it once and twice. Therefore, you can understand how to draw the layout for this one. Okay, we stop here today, and we will see the remain this in the next class. Thank you.